again.
Hi everyone, welcome to this exciting World Space Meet talk show series where we are going to explore the role of geology in space science and India in space race. I'm your host, Bharti Sharma, geologist and founder of AADYA Planetary and Geoscience Research, a trailblazing organization in the field of geotourism and collaborative research, a startup that deals in geoconsultancy and skill development as well. Today, we have a truly remarkable guest with us to shed light on the captivating interplay between geology and physics and their role in space science. I am honored and privileged to share my screen with Dr. Pavithra Sekhar, Assistant Professor at the Center of Excellence in Astrobiology at Amity University Mumbai. She did her bachelor's and master's in physics from India and later went to Virginia Tech, USA for her PhD in planetary geophysics. Her research interests lie in planetary analog studies and impact craters. Welcome, ma'am. Thank you so much for coming.
Hi, Bharti. Thank you so much for having me here. I am so happy and honored to be a part of World Space Week, especially, in such a format where I can talk about planetary geology, geophysics. And I hope this is a very enlightening session. I look forward to this.
Thank you, ma'am. So, to begin our discussion, my first question is what are some of the, why you started planetary geophysics? What drew you to this field? What was the inspiration behind?
Okay, so you'd be very surprised that this wasn't planned at all. In the sense, I had no specific direction that I wanted to go at early on. I wasn't looking for a call or a purpose. But it so happened that my physics teacher, when I was in school, in higher secondary school, my physics teacher was the one who really got me fascinated into space. And as cliche as it sounds, my path has not been one straight path at all. I started somewhere completely different and I ended up completely different, but I've always been able to live up and want to, pursue planetary science. So what drew me into the field was initially, it was just space. And at that time when I wanted to pursue a degree, physics was the most common sort of field that was closest to space. So I decided to dabble in that. And I wasn't looking to, do physics, but it just happened. And when I started physics, I got introduced to astronomy and astrophysics. So that really fascinated me, space, understanding stars, and, all those fascinations that people always talk about. And gradually, I ended up doing projects in astronomy and astrophysics with Birla Planetarium in India. And then from the star system, I decided that I wanted something a little bit more, understandable. So I started moving more from the star system to the planet system. So when I moved to the planet system, I was super fascinated with especially the rocky planets. Not and gaseous giants are also very fascinating, but for me personally, it was the rocky planets. So with that interest, I decided to pursue in planetary science with a very strong physics background. I also knew that I wasn't very keen on getting a PhD in just pure physics, but I wanted to have an interdisciplinary field. So I thought what would be the best that would combine with it. And I was fortunate enough to actually have that opportunity at Virginia Tech, where my advisor was actually a planetary geology and geophysicist. Now, you'd be very surprised to know that I knew nothing about geology and geophysics at that point because I came from a pure physics background. So I was introduced to it. Initially, early on, it was quite challenging because I didn't know a lot about the rock structures, the geology, the importance of geology, especially in planetary science. I was a little new to it. So my PhD advisor was very understanding and he kind of supported me with a lot of the geology aspects of it. But then once I understood the importance of rocks, geology, the systems, the geologic time scale, especially on different planetary bodies, I got very fascinated with how all planets formed at around the same time but are entirely different from each other, at least to a large extent. So then I was interested more in volcanic processes, even when I was studying geology. So I was very fascinated with volcanoes, the types of rocks that you get, whether it's a hot spot, whether it's a tectonic plane driven volcano, all of those. So that led me to working on a project on Mars. So trying to understand the volcanoes on Mars. And that was my core in during my PhD. So my planetary geology, geophysics became my core at that point. So physics was still very important, but without the geology, it just wouldn't mesh together. So Mars volcanoes, the crust, how it formed, the crustal dichotomy, why was it important? At the same time, what was happening at the interior of the planet. So the physics involved with that became very crucial to understanding that. Um, and then when I was doing volcanoes on Mars, I got very fascinated with the crustal features of Mars. And I noticed that there were a lot of craters, a lot of impact craters. And it kind of fascinated me to see that they were so old and what kind of features do you see in these craters. So after my PhD, I pursued a postdoc, but I moved from much more of the interior of Mars to the surface features of Mars. So that's where my analog studies came into play. And then studying impact craters and then studying, the hydrothermal systems. That is, if you had a heat-driven system, whether it's an impact crater, whether it's a mid-Atlantic ridge, how does that help? Is it important to understand the evolution of a planet? And in recent years, that's been a key field for astrobiology as well. So if you have these kind of thermal driven systems, and if you had them early on Mars because of the impact craters that we've seen at the volcanic activity, maybe there could have been some kind of possibility of fluvial features, which in turn ties into astrobiology. So even though I'm at the center of excellence in astrobiology, I think my background is I'm very lucky that my background is actually very diverse. And as you can see, it was a decision that kind of changed at each stage to be, flexible to learning new things, but at the same time, not forgetting your main core, your main passion. If you had to move from a pure science field like physics and then combine that with geophysics, and then after that, learn a little bit of biology, like topping on the cake, to try to like connect all of those things. So the thing is, it wasn't a straight path, and I was never like, okay, I have to do this. It was just pure fascination, and at every stage you make a decision and you just hope that it leads you to the right place, but your ultimate goal and your passion should be the one that drives you. So that was the main reason, and that's how I came into this field.
And we are happy to have you here. Finally, you have a really great planetary geophysicist. So, what are some of the key questions you are currently exploring in the field of planetary geophysics in your lab?
Yes. So at the Amity Center of Excellence in Astrobiology, we have started a master's course in astrobiology and space sciences. This is the first semester actually, and it's going quite successfully because yes, we've been able to introduce my specialties plus the other faculties who are in the department. So you get a biology, a mix of meteorology, a mix of geology, mix of physics. So it's kind of got a very good combination of all the keys that we actually are strong in. So at the center as such, we come under the Amity Institute of Biotechnology. So definitely biology is a big part of it. But as I mentioned, some of my research projects and interests are with hot springs. So for example, the Puga hot spring that is in Ladakh. What kind of extremophiles or organisms live in that kind of system? So when you talk about the extremophiles and the organisms, that's where the biology becomes an important part. But when you need to understand how the system has evolved by itself, from underneath, what kind of a heat source, what kind of a magma source do you have? That's where you get the geophysics and the geology part of it, because that ties in. So a lot of my key questions are, if we had a thermal system early on, because we didn't believe Mars was a dead planet early on, if we did have a thermal system, and if we did have, these kind of thermal systems, can you actually envision some form of organisms? Maybe life is a little bit of a stretch, but the survival of organisms, microorganisms in that kind of environment. And the other thing also is, as I mentioned, impact craters. So taking an understanding of impact craters like Lona Crater here in Maharashtra or Chesapeake Bay in the US, trying to do a comparison of those impact craters, trying to see the crater system we have on Mars, like the Jezero crater, or even the craters that we see on the moon, which was one of the recent missions that we also had going on, the Chandrayan 3 mission. So craters are very important because on a geologic time scale, from a geophysics aspect, from an astrobiology aspect. So this is another thing that I'm very interested in, and I am working on a little bit of modeling and simulation because I'm a computational modeler, but I strongly believe that field work is also crucial for this kind of modeling because you should be able to connect the two.
Field
Uh,
data is obviously important.
Exactly. So just being a computational modeler makes it very difficult, but at the same time, just doing field studies, for me, it has to be a combination of the two. So impact crater systems, hydrothermal systems, on planetary analog studies. So if we can understand on Earth, can we apply a similar system on another planetary body, whether it's a moon, whether it's Mars, whether it's any other planetary body? Can you get some insights maybe into the evolution and so on? And one interesting thing I want to mention is there are a group of scientists also who believe tectonic plates could also be a place to look for when you talk about organisms. So that's a entirely fascinating field that's kind of, coming up, and it's been there for a while, but it's gaining a little bit more. Why not tectonic plates? Why can't they be one of the reasons for it? So yeah, so that kind of ties in. So it's a lot of modeling, a little bit of field work connecting the two, and then collaborations to apply it to astrobiology and see what kind of fascinating answers you can get from that.
That's great. I strongly believe about the field studies and the computational modeling. And also, planetary science is not just engineering right now, it's planetary geology, planetary geobiology, and celestial biology. So, there are multiple ways to enter space science. Well, I would like to, if you could shed more light on crystal diaptomy on Mars.
Yes, sure. Um, so in the case of crustal dichotomy of Mars, it is one of the most important features that we see on the surface of Mars, and it was sent very early on, 3.5 billion years ago. And Mars is believed to be a one-plate planet. So we don't necessarily see, kind of the mantle subducting, or sorry, not the mantle, the crust, the lithosphere subducting, and we don't see any new material coming from its side, except through the volcanic features on the surface. So the crustal dichotomy on Mars makes it very unique because there's such a huge difference in elevation between the southern highlands and the northern lowlands. So the Jezero crater, for example, is kind of in the cusp of this. So you get to, understand why something like this happened also. There is, a general in the scientific community that we had a huge impact 3.5 billion years ago that created the crustal dichotomy. And even within the crustal dichotomy, you've got the largest valley, which is Valles Marineris, which is on Mars. We've also got a basin, which is Hellas Basin. And of course, we've got Olympus Mons, the largest volcano of the solar system. So if we had a volcano that is, 3 times the size of Mount Everest, then how did it form such early on? And what happened after a certain amount of time? Did it completely stop, or do you still have kind of isolated volcanic activity? So without tectonic plates, we believe the hypothesis is probably a plume. You have a hot plume that comes just from underneath, makes it to the crustal surface. And then because of the different viscosity, for example, on Mars, they're all shear volcanoes. So the viscosity is very different from the viscosity from a lot of volcanoes here on our planet. So the crustal dichotomy clearly gives you that difference, so which can also impact how much material comes from underneath the surface. So from a geophysics perspective, it's very interesting because if there's such a huge difference in thickness of crust, especially the Tarsus region, which contains the most volcanoes. The crustal thickness is so dense. It's so dense that it's kind of hard to see or hard to fathom how the material actually makes it to the surface. And so, it's kind of very fascinating in that way to kind of see why Moon doesn't have something similar to that, or why our planet is so different.
So, do you believe Mars is still an active planet or a dead planet as per the planetary geophysics?
Yes. So that's a very good question. There are much more than the scientific community, I hesitate on saying completely dead. One of the main reasons for that is we still see isolated volcanism in recent years. And of course, you would know this on a geologic time scale. Recent years is still like 200,000 years. Yeah. So the thing is, whether there's a lot of internal activity is, very questionable, because it doesn't have a magnetic, it doesn't have a magnetic field and so on. But whether it still has these isolated spots of, activity, or, what is the reason for this kind of isolated volcanic activity, states that it may be a dead planet with the possibility of pockets of hotspot activity. Because according to us, everything that we relate in planetary science is based on our planet, how it's evolved. So that is our base and our foundation that we are applying to other planets. So it's not necessarily that has to be the exact, one single belief of how different planets evolved, right? So Mars is, I want to say, comparatively dead planet, but it definitely still had and still has, or at least on a geologic landscape, still has volcanic activity. And that still leaves some question in doubt, whether there is a possibility of some kind of activity maybe in the topmost parts of the planet.
So there are like endless knowledge gaps when it comes to Martian geology.
Yes, definitely. That's why even with all the missions, for example, the InSight mission that NASA had on it, it detected tremors, or like people would like to fascinate, like Mars quakes. So how did these, if Mars was an entirely dead planet, what it's causing these tremors, right? It shows that yes, it is a one plate planet, so you don't see breaking of the lithosphere for subduction, but it still means that there's some kind of activity possibly going on for you to even detect these tremors. So which opens up the question as to how, why, where, what's fueling this.
That's a fascinating insight from you about Martian geology. Now I'll shift gears towards the historical movement of Chandrayan 3 landing. So how do you see India's contribution and achievements in the field of space science evolving in the coming years?
That's also a very good question, and I'm so glad you asked that, because ISRO and the Indian space missions, especially in the last month or so, has it's been fascinating and amazing that we've been able to achieve a lot of the things that we had been planning for a really long time. And not just Chandrayan 3, even the AADYA L1 mission to the sun. So with respect to planetary geophysics, I think Chandrayan 3 was definitely the first step, especially because of the South Pole.
Yes.
So again, this is also very fascinating, and this is something I'm also looking into a lot more, is the importance of South Pole. Being one of the first countries to land on the South Pole, especially with such huge temperature differences. I think, the understanding that we've had so far is, again, the crater system. And, the possibility of permanent ice, because it's never seen, the side of the sun. And it's kind of, it's just remained there for a really long time. I think can again tell you more about the history.
Yes.
It can also lead to maybe the possibility of this water ice interaction. So these craters, even if not the entire crater, one part of the crater is believed to have this permanent water ice permafrost layer. So Chandrayaan 3 mission, the South Pole is very challenging, as a lot of people know, to land. So I think the fact that we landed there, and one of the first elements we discovered was sulfur. So again, when you think about sulfur, begs to differ the question: if it's sulfur, then where did that sulfur come from? Right? So it's kind of fascinating, but I definitely feel it's in the right direction. And with the possibility of a Chandrayaan 4 mission, which would be done with JAXA, possibly in the next, with ISRO, it's hard to pin on a time, but I want to see within the next year or two, which would be the Chandrayaan 4 mission, the possibility of that happening, I think would definitely be amazing, because hence the geology. It also talks about the crater system. It also talks about, if you have sulfur, maybe it's not such a bad idea to look for organisms that need sulfur for survival, or what could be some of the combinations or the possibilities of that. So with ISRO, that is definitely something, especially with the moon. So that was a super proud moment, and especially the upcoming mission. Other than that, I think for the possibility of a mission to Venus, which has also been planned, is would be very, very important. Again, for astrobiology, a lot of people picture only water or compounds of water to be an important source, but maybe that is not necessary. I mean, the chances are much higher, yes, because again, we are basing that on our knowledge. But
We know remotely.
exactly, what if the clouds of Venus had some kind of compound structure which could it help? Could there be a possibility of, that's why I said I try to use the word life in a very light term, but I rather prefer using organisms or microorganisms. Could they survive? So the Venus mission that we've got going on, the Chandrayaan 4, will definitely will tie into astrobiology quite a bit. We also got the Gaganyaan mission, which maybe not that much into planetary geology and geophysics, but still, in collaboration, I believe, with Soviet Union, if I'm right, where, they train astronauts. And so that will be also one of our pivotal missions to see if we can send people up there. So I think everything is very fascinating, because you can have engineering problems, you can have science questions, you can have astrobiology, you can have planetary geology and geophysics. You can also, whether it's, even space health.
Yes, space psychology.
Space psychology, space health. So it's all like a combination of all of these things. So I think India's contribution, especially now that we're in a space race, and especially now that our government has been supportive, and now I believe that is the prime time to catch on that support, because we've had these successful missions going on. So to not lose that steam, and to push forward, to make sure that we keep up and then we maintain, I think is very important. And collaborations, as much as we work alone together, I think it's important and very crucial for us also to get collaborations with other places, because in the long run, human race, or you're trying to think of how to contribute to science, whether it's US, whether it's Russia, whether it's Japan with JAXA mission. It really depends. So I think for India, this is like a great start, and I think I definitely feel strongly that we pick up, and we look for those possibilities.
Yes, and I strongly agree with you on the collaborative approach towards space. As we all say in space science, that space is for all, and we actually need it.
Right. Yes.
So thank you so much, ma'am, for sharing your thoughts on the Indian space missions. And now moving to our last question, but very important for our audience, that is, what advice would you give to university students or early career researchers who wants to pursue a career in planetary geophysics and contribute to space research?
Okay, so so this is something to all the people, all the students out there. again, it might sound very cliche to a lot of people, but honestly, my first suggestion is, if you are genuinely passionate about what you do, don't worry about how quickly you reach the destination. For a lot of people, it can be a long, winding path. For some people, it may be a very, quick path. For some people, it may appear, and then later on they realize that's not where their true passion lies. So one of the first things I want to say is, you have to be patient, but you also have to have that passion and then drive inside of you. Because if you take my story, the fact that I started with the passion in space, that's it. I didn't know at that point that I want to be an astrobiologist or a planetary geophysicist, but introducing those subjects, later on. So it kind of took a long-winded path, but I learned so much on the way. So I was always in space. I was always in planetary science, but my discipline changed from time to time. It was physics, then geology, geophysics, now astrobiology. So I only say that, keep the dream alive, pursue the best, what you can. Don't give up hope, because these days there are also a lot of opportunities out there, because planetary geology, geophysics, by the name itself says that it's interdisciplinary. So you can come from any background, and I'm telling you this even because we started this master's course. You can be an engineer, you can be a science, you can even be in space management, you can be in business school, you can have planetary protection, you can have, any kind of fields of sciences, planetary geology, geophysics. So for planetary geology, geophysics, don't narrow yourself so much, because I know a lot of students these days feel the pressure that they have to know where they're going right now. Sometimes it's not that black and white. So keep a little bit of a gray area. Keep your main passion up there and be open to different opportunities. You will reach there ultimately. Don't worry about it. But have those opportunities open, pursue them, and, one way or another, especially with this field that's evolving so fast. Even missions to Uranus, Neptune, Ceres, Pluto. We also have, missions to certain types of asteroids, Psyche mission, which is going to an entirely different type of body. So planetary geology, geophysics, especially, I feel, is very important. So I think in whatever field of science you are, you can tie that into planetary geology and geophysics. If you're an engineer, you still have to know the geophysics and the geology of a planet. If you're an astrobiologist, you still have to know the geology and geophysics of the planet. So yeah, so just be patient, stay true to yourself, and you will reach there. Just don't be in a hurry to know everything when you open the book. Like, it's like wanting to read the last page of a very good novel without going through the entire book. So take your time, reach there, but have your passion and your drive, and everything will be good.
So it's okay to have an unconventional path in your...
Definitely. It's perfectly okay to have an unconventional path. The only thing is, at every stage, you will be responsible for your decisions, yes. You have to be a little bit flexible to learning new things, but always have that core belief of whatever you're interested in. Have that flexibility, which may be a temporary field, or which may be something that was super fascinated after you get introduced to it. So like I said, I don't have a biology background, but I have the Center of Excellence in Astrobiology, because it still has implications in biology. So you can learn. There's no issues at all. Just have that drive and passion. You'll reach there.
Sooner or later, maybe we'll be doing an interview on planetary geobiology.
Yes, I definitely see that happening. I definitely see paleo, geo, multiple parts of, so we'll combine all of them together.
Thank you so much, ma'am, for sharing your insights and expertise. And a big thanks to our viewers for joining us on AADYA Geo Talks. Remember, the conversations don't end here. So stay curious, keep learning, and make a positive impact in your own unique way, in your own unconventional way. So until next time, take care and stay tuned for more enlightening discussions. And don't forget to follow us on LinkedIn, Facebook, Instagram, and YouTube. Namaste. Thank you, ma'am.
Thank you.